Hello, welcome to Section 8.2, the basics of hypothesis testing. I strongly recommend that you go to your multimedia library and print this PowerPoint. Then you can take notes as we proceed through this information. This information is critical because you will be looking at hypothesis testing in both chapters 8 and 9, as well as understand that it could be used in subsequent chapters as well if we wanted to check and test different claims. So we're going to learn about the null hypothesis, the alternative hypothesis, how to write a claim, how to express them symbolically, how to find the test statistic. We will be using StatCrunch for that, how to choose the appropriate distribution, whether it's for the proportion, the mean, or the standard deviation, how to identify what we call the P-value or critical values, and how to write the conclusion about a claim in simple, non-technical terms. A hypothesis is a claim or statement about a property of a population. This would be either a proportion, a mean, or a standard deviation. The hypothesis test is the procedure we follow to test the claim about the mean, proportion, or standard deviation. Similar to doing a lab in science class, where you follow the scientific method, here we follow the procedure for the hypothesis test. If we find that the probability of a particular observed event is exceptionally small, we will conclude that the assumption is probably not correct. So if something's only happening 2% of the time or 0.5% of the time, we're going to kind of assume that the assumption about that is not accurate. We start off by talking about what is called the null hypothesis, denoted by H sub 0. This is the statement about the population parameter, again, proportion, mean, standard deviation, and we're making a claim that it's equal to something, to some value. So we're going to test, is it true? So we fail to reject it, or is it false and we reject it and assume something different? Again, we're looking at the null hypothesis, and there's always a statement about equality. The alternative hypothesis is denoted by H sub 1 or H sub A for alternative, and this is the statement that the parameter has a value different from the null hypothesis. For example, let's assume that our null hypothesis was that the mean on an IQ test was 100. The alternative hypothesis then could be one of three things. We could say the mu is greater than 100, mu is less than 100, or mu is not equal to 100. If you're conducting a study and you want to use a hypothesis test to support your claim, you're going to have to word your claim so that it becomes your alternative hypothesis. You can read over these steps, just summarizing what we've looked at so far, and we're going to take a look here at a quick example. So there's an XSort method of gender selection being used, and couples are going to try this method out. So they have their babies, 100 couples have 100 babies, and we find that there are 58 girls in those 100 births. So we want to test to see if the proportion of girls is greater than 50%. How would we write it? H sub 0, P equals 0.5. H sub 1, P is greater than 0.5 because the claim is that the proportion is greater. The next thing we're going to do is select the significance level alpha. This is just like the prior chapter where we were looking at doing confidence intervals. Typically, alpha is 0.01, 0.05, or 0.10. You want to keep it small because it's the chance of what we call a type 1 error, the chance that you would falsely reject a true HO. These are the particular test statistics, similar to the last chapter, that we're using when we do hypothesis testing. Again, the software is doing the actual computation for us, but we need to know which one are we using. If your problem is talking about percentages or proportions, then you're going to choose the proportion test. This uses a Z distribution, and of course the requirements are NP greater than or equal to 5 and N times Q is greater than or equal to 5. If you have a problem asking you about the mean, and sigma is not known, but you do have a normally distributed population, or sigma is not known and you have a large enough sample, meaning it's greater than 30, you use a T distribution. If, however, you have one of the rare problems where sigma is known and you have a normally distributed population or a sample greater than 30, then you can use Z. Lastly, if you're looking at a problem about standard deviation or variance, then you're going to do a chi-square distribution. The requirement there, of course, is extremely strict, and you must have a normally distributed population. So first we're going to find the value of the test statistic using software, and then we can take a look at what's called the P-value with our software, or occasionally critical values. So we're going to go back to the test where the couples are having their babies. They had 100 couples, 58 girls. And the null hypothesis was that the proportion was 50%. The alternative is that it's greater than 50%. So we take a look at our sample proportion. Remember, the sample proportion is denoted P hat to keep it separate from the population proportion, and we know that that's 58%. When we use software then to compute this, or in this particular case, doing it by hand, our z-score is 1.6. Now, if you recall from when we looked at the chapter with the empirical rule and talked about range rule of thumb, a z-score between -2 and +2 is pretty much common. That's not unusual. So a z-score 1.6 is not unusual, and it really looks like 58 girls out of 100 births doesn't really support the claim that this particular gender selection method really works. When we're talking about a distribution, we can be talking about what are called the tails, which are the extreme regions at the end, where we would say that the values are significant. So we need to know whether it's a one or two-tailed test. If our claim is that something equals, for example, the mean equals 100 and the mean is not equal to 100 as our alternative claim, then we could prove or disprove, high or low at either end. We could say it's a lot higher than 100, or we could say it's a lot lower than 100. The way we know that this is two tails is because the claim is that it's not equal, so you could go to either side. If, however, the claim is that it's less than, then you're going to see the little left-hand tail shaded, or right then, you'll see your right-hand tail shaded. Now, our software will be helping us compute what's called the P-value, which is short for probability value. That's the probability of getting a value of your test statistic that's at least as extreme as the one you got with your sample data. In other words, what's the probability that if you repeated this again, or if you sampled the same population, you would get results at least that extreme, or even more extreme than what you determined? What's going to happen is we'll reject our null hypothesis if our p-value is very small. So, for example, you can use a little rhyme to help us remember. If the p is low, reject HO. If the p is high, let your null fly. So if your p-value is small, like 1%, 2%, 3%, and your significance level was 5 or 10%, then your p-value is small enough to be significant and you reject HO. If we go back to the example we looked at before, the p-value was 0.0548. The chance of finding more girls out of the 100 or finding results more extreme was 5.48%. Here's a quick little chart to help us summarize the procedure for finding p-values. And again, the software really helps us do this, so it's a great tool. But keep in mind, you can refer to this chart to help yourself clarify, is it a one or two-tailed test, is it left or right hand, and how do I interpret those results? If the question asks us about what is called the critical region or the, quote, rejection region, then we're going to take a look at the values that separate our test statistic from the regular or usual range compared to the not usual range. So for example, if we claim that the significance level was 0.05, meaning that we were willing to tolerate that 5% of error, we were only looking for the values greater than 50, of course, that would mean that the entire 0.05 was in the top end of our distribution. We would use the normal calculator like you did in Chapter 6 to determine the z-score that marks off the top 5%. In this particular case, it's 1.645. Okay, so very quickly, you're going to go to StatCrunch, and you're going to log in, or click to it from your homework question, and you're going to open up your calculator and click normal. So again, we're going to go to normal here. We're going to say, what is the z-score that cuts off the top 5%? And you can see it's 1.645. That's what we're referring to in our slide. What that means is that your z-score in your computed problem for your sample data would have to be larger than this value in order to be considered significant. If you recall from the gender selection method, our z-score was 1.6. It was not greater than 1.645. We're close, but we did not get a significant result. Okay, keep in mind, quick cautionary note here, that the p-value is the probability of getting a test statistic at least as extreme as the one we got. A lowercase p stands for the population proportion. Don't confuse the two. Now, let's assume that we got a critical z value, that it got into that little shaded region at the end of our distribution, or our p-value is really tiny. What do we do with it? That means then that we reject HO. If our p-value is less than alpha, we reject HO. If our critical z is smaller than our calculated z, we reject HO. Or if our z-score is negative and it's below the negative critical region, we'll reject HO. Here again, if the p-value is less than alpha, less than or equal to alpha, reject HO. If it's greater than alpha, you fail to reject HO. We do not use the terminology accept. We simply say we reject or we fail to reject. Kind of like in a court case where they might say, this particular defendant is proven guilty, or this particular defendant is found not guilty. Typically, you would have to work very, very hard to say that they're innocent, because there may always be a shred of a doubt or lack of information to help you choose that option. Here again is the example. So then we want to restate the decision using simple terms. For the XOR baby gender test, there was not sufficient evidence to support the claim that the method was effective in increasing the probability that a couple would have a baby girl. This is a great slide. You definitely want to keep this handy as you work through your homework problems and you try to determine, how do I word this? Which answer do I pick? A lot of times students tell me it's not the computation, it's not even selecting the right test. It's those last couple of questions on the homework where you're trying to figure out which conclusion is the correct representation of our results. Is there sufficient evidence to warrant rejection of the claim? Is there insufficient evidence to warrant rejection of the claim? Is there sample data or is there not sample data? Okay, and again, we've already mentioned the idea of accept versus fail to reject. We reviewed type 1 error, the mistake of rejecting the null hypothesis when it's actually true, and that's alpha. A type 2 error is another one that you don't want to make, and that's the mistake of failing to reject the null hypothesis when it was actually false. A little chart that summarizes this for us. So a type 1 error in the gender selection process would be that you would reject HO and assume that the proportion is greater when really it wasn't. You would be saying, oh, this method works, this is great, there's going to be more girls, when really that wasn't the case. A type 2 error would be that it really is working, there really are more girls, and we didn't see that. We didn't find that, but it wasn't our results. For any fixed alpha, if you increase your sample size, you'll decrease your beta, your type 2 error. If you fix your sample size, if you decrease your alpha, then beta is going to increase, or conversely. If you want to reduce both type 1 and type 2 errors, then you've got to make your sample size larger. And again, we talked about that back in the beginning. If you want to be more precise about your results, then you're going to have to increase your sample size. Now, one other concept here that we don't talk about a whole lot, but I want you to understand, is the power of a hypothesis test. So if you know, for example, that there's a 20% chance that you would make a type 2 error with beta, then the power of the test would be 1 minus 0.20, or you would say 80%. So you'd have an 80% chance of rejecting a false null hypothesis. Software computes these kinds of things for us, but I just want you to understand the idea of power, because it has a very close link to the design of an experiment. When you design an experiment, you want to consider how much of a difference between the claimed value and its true value is important to you. Do you want to be different from the population value by 2%, 5%, 10%, or 5 points, or 10 points, or different how? So you want to think about that claim difference, and that helps us as we design an experiment. The goal is, of course, to always have a power of at least 80%, and then that helps you determine the minimum sample size that you would need to use. Again, we don't get into a whole lot of research design, but it is important to understand that. Now, in order for you to understand how to begin doing your homework on StatCrunch, keep in mind that there are 2 other videos for Chapter 8. One is a longer video where it would walk you through homework problems and how to work them out in StatCrunch. The other is a shorter video just walking you through a very quick review of using StatCrunch to complete your homework. Remember, at this point, we're currently focusing at proportion statistics, t-statistics, very rarely z-statistics, or variance statistics when we're talking about standard deviation or variance, and we want to use the chi-squared. To compute critical values, however, you're going to go to the calculators. And again, this is also reviewed in other places, both in writing and on my video. But for example, let's assume that we had a two-tailed test and a t-distribution, and we had sampled 35 people, so our degrees of freedom is 34. And we want to know what's the cutoff for the bottom 2.5% and the top 2.5% for a total of 5% error. So our alpha is 5%. If our computed t would fall below a negative 2.03, or if our computed t fell above a positive 2.03, notice they're symmetric because the t-distribution is symmetric like z. If our t fell below a negative 2.03 or above a 2.03, then we would have grounds to say that our results are significant. In other words, our p-values are going to come out really small. Keep in mind that is finding what is called critical values, and there's more about that in the other video. Good luck!